Good evening, friends, and warm welcome to another exciting episode of Curious Minds Online, and a special welcome to the very large contingent that we have this evening from St Andrews University, who've come along to watch the home team play. So glad to have you in Perth, and glad to have you taking part in a PSNS event. This evening, our speaker is Dr. Nick Gardner of St Andrews University. He is a geologist and a geochemist. He studied in Leeds and Oxford and has taught in Australia. But he spent the last few days in Glasgow attending COP26 on behalf of the Geological Society. So he can certainly demonstrate that his subject is well up to date and relevant to all of us today. This evening, he's going to be speaking to us about plate tectonics. Some of us earlier, as we were gathering, were recalling how we can all remember hearing about this back in the 1960s, when it was still a fairly new idea and just on the point of becoming mainstream orthodoxy. Dr. Gardner will be telling us about the history of the idea and about how our planet works. As usual, there will be a question time in the end. If you think of a question, you can use the chat function on Zoom to send in your question whenever you think of it. You don't have to wait until the end. And we can then serve up all these questions to Dr. Gardner at the end of his talk. So I'd now like to welcome Dr. Gardner and hand over to him. Thanks very much.
Thank you, David. Can everyone hear me? Am I clear? All good? Excellent. Thank you everyone for turning up to listen to my Friday evening thoughts and for the talk. You know, I wish I could be there. The original plan obviously was to go there in person, but events interject, and here we are. But it's great that there's a great turnout. I'd like to thank Tom for the original invite. We had a chat probably 6 months ago. This was when the diary was empty before I ended up going to COP, so it's been a bit of a mad week, but it's fantastic to be able to talk to you all about some of the research that I do and what I think is a really exciting and important subject in geoscience, and one that didn't get the airing it should do at COP, but that's a different matter. Thanks also to Michael for you with this. So I'll try and share my screen. So the remit really of the talk was to talk a little bit about plate tectonics. I'm largely a geochemist. I've tried to keep it more at a really sort of, there's a historical aspect as to how the idea of plate tectonics came about, what it is, and also how we transitioned from an Earth that clearly or probably didn't have plate tectonics to one now. So I'm going to talk about sort of a history of the Earth as well. There's quite a lot of material. I'll try and keep it clear and at a high level, but obviously there's question and answers at the end. So if something's unclear or you want to quiz me, we can always go back and cover something, but I'll do my best. So let's share the screen. Okay, can you all, is that good and clear? Yeah. Okay. As I said, I'm going to turn off my camera because how do I do that? Now I've lost him. I turn off my camera because the internet connection is not great, but hopefully you can still hear me. Okay, so plate tectonics is fascinating. Let me go to the next slide. Right, here's Venus and the Earth. So the Earth is unique in the rocky bodies of the solar system and unique as far as we know in the universe in having plate tectonics. This is to kind of demonstrate that Venus and Earth are very geologically similar. Obviously, they occupy different positions in the solar system. But some people will sometimes refer to Venus as Earth's evil twin. It's similar in size. It's geologically very similar. It's compositionally very similar. But it is a completely inhospitable different world with a surface temperature of 400 degrees C plus. A runaway greenhouse effect has caused this. It's geologically very inert. And it is a very different world. And plate tectonics is one of the things that makes Earth absolutely unique. And it's so special, not in terms of its geological and physical properties, but in terms of its habitability, because as we'll understand, it drives the circulation of elements between the interior of the Earth and its exterior. It provides platforms for life to develop, and really it's kind of the framework within which we understand the Earth. And as some people were saying earlier on, you know, it's actually quite a young theory or a young hypothesis, but plate tectonics is geoscience's great unifying theory. And you know, I think it's every bit as profound as, say, the theory of natural selection. Darwin himself was actually a geologist, or the theory of relativity. It's kind of the geoscience version of all of those. And it's one of these theories that when it was formally described, again, only in the late 60s, really, everything sort of clicked into place. So evidence from the fossil record, from the rock record, through to the distribution of earthquakes and volcanoes, the topography of the continents, the bathymetric topography of the oceans, the age distribution of rocks. So almost all the geological evidence suddenly clicked into place once plate tectonics and the theory around it had been formally described. It was absolutely phenomenal. But yes, it was only fully accepted 50 years ago, so it's still relatively young. There are practicing geologists today, as we've heard. There are people here today who can remember when it was sort of still coming about and was still crystallizing as a theory. But you know, I teach geoscience here, and it's unimaginable to teach geology or geoscience without the context of plate tectonics. It's absolutely the framework within which everything geological is developed, and it's the driver and the instigator for much that is geological anyway. So let's look at some sort of basics about the Earth. This may be revision for some, but it's worth going through. So this is a sort of cross-section through the Earth today as we see it. It's about 6,000, just over 6,000 kilometers in radius, and it's a compositionally layered planet. It's a rocky planet. It's largely silica in composition, but it is internally layered, and this reflects not only its original formation, but also its evolution. Because the process of stratification, and we use the term differentiation, comes about through the evolution of the planet through its life history. But you know, rocky planets, or all planets, originate through the condensation of material as the solar system cools down. So the Earth has a solid core. This is largely made of iron nickel alloy. It has an inner and an outer core. The inner core is solid because the pressures are so high. The outer core is still a liquid, and that's what gives us our magnetic field. Then we have a mantle, which is largely of molten rock. It's peridotitic, that's the phrase of composition. It's a sort of quite primitive type of rock that's largely molten, and it undergoes slow overturn. And then we have a crust, and the thickness of the crust is minuscule compared to the radius of the Earth. It's up to maybe 100, 150 kilometers thick, could be as thin as 6 kilometers. So, you know, we can liken the crust to the thickness of an apple skin on an apple. It's relatively, you know, it's really thin. And an important concept when you learn geology is this idea of the difference between continental crust and oceanic crust. So again, we're right here, up here at the top of the pile of Earth's layers, and there are significant differences compositionally and rheologically and otherwise. And oceanic crust, which is on the right here, let me see if I can. I'm just going to try and do this is pointer options, laser pointer. Can you see that? There we go. So on the right here, oceanic crust here is kind of highlighted. They use a dark color, but it's largely basaltic in composition. So it's relatively dense. It's relatively, we use the term mafic, so it's silica poor, and it's thin. It's about 7 kilometers thick on average. Continental crust, which is what we live on, what our mountains are built on, what our towns and cities are built on, what is emergent above the oceans, is different. It's granitic in composition. It's silica rich. It's much thicker, on average maybe 30, 40 kilometers thick, but it can become much, much thicker, up to 200 kilometers if we're looking at things called cratons. And it's buoyant because both oceanic and continental crust exist above the mantle, and they are buoyant upon the mantle, but the continental crust is much more buoyant. We use this term lithosphere here. I mean, there's lots of jargon terms, but lithosphere is basically the top part of the mantle and the continental crust, and it's kind of the rigid outer layer that deforms together and is usually locked together. So if you hear the term lithosphere, it's just it's sort of, well, it is the crust and a little bit of the mantle, but this is all buoyant upon the mantle. So continents host mountain belts. As you can see, oceans are in the abyssal plains. And the other thing that's interesting about them is we have an age distribution. So this little chart shows us the age of the continental crust. On the right, there's a timeline. This is kind of roughly the Earth's, let me just try and, sorry, in this zoom, all I can see is okay, right. On the right, we can see the Earth's timeline. So we're going back to, the Earth is 4.56 billion years old. These are in gigayears. Going up to the top, up to today at the top. So you can see the Hadean era. These are the different geological eras on the right: Hadean, Archean, Proterozoic, Paleozoic, etc. And the Earth's continental crust, the record that we have at present, goes back to about 3.8 billion years. So we have a range of age of continental crust back to 3.8, not back to the dawn of Earth, because we don't actually have any surface material or any terrestrial material that we can date back to the formation of the Earth. But the oldest continental crust is about 3.8 billion years old, and we find that in West Greenland. We use radiogenic isotopes to date rocks. I'll talk a little bit about that later. We actually date the Earth through meteorites because we assume that meteorites formed at the same time as the Earth. As I said, we don't actually have terrestrial material that we can date back to the dawn of the Earth. But what you can see in terms of the age distribution pattern is that, and so these are the ages on the left. Archean is dark blue, so that's the oldest, going through to red, which are the youngest crust. You can again see an age distribution. So if we look at North America, we can see these sort of very old cores surrounded by a progressively younger crust. And in North America, the youngest crust, the youngest continental crust, is to the west. If we look at Europe and Asia, we can see a very young seam of crust that comes through here, through the Alpine chain, through the Himalayas, for example. And then up in Scandinavia, you've got much older crust. We've got some older crust in Australia as well. So there is actually a pattern to the age distribution of continental crust, as well as the fact that continental crust is generally a lot older. If we compare that to, here we go, oceanic crust. So oceanic crust is, it's very different. So again, this is age distribution of oceanic crust as we understand it today. You can see that we're going from young in red to old in purple through the blues. But the oldest oceanic crust that we know is about 250, maybe 300 million years. And on the timeline, we're just up here. We have nothing that's really older than that. So oceanic crust is much younger than continental crust. And as we talked about, not only is it much younger, it's compositionally different, and it's less buoyant. And so we have a sort of, I can't remember the term actually, there's a geological term to tell you about sort of the bimodal distribution of crust. That's probably a good term, the bimodal distribution of oceanic versus continental crust. So the historical perspective of plate tectonics, I mean, that's a bit of an introduction to sort of the Earth as we see it. Goes back a long way to the early map makers. I quite like this map. This is 1541 from a German physicist called Lorenz Fries, and this is a map of Southern Africa. And I just think they actually did a pretty good job in those days. But this is a map from 1596. So the first map makers, the first cartographers noticed really similarities in continental profiles. And most strikingly, especially around the Atlantic. So they noticed that the African continental margin was very similar to that of South America. Similarly, in Europe, you could say there were similarities in the margins along here. So Abraham Motilius was a Flemish cartographer, and he wrote in his, perhaps it was his magnum opus, it was certainly something that he wrote, Thesaurus Geographicus, that the Americas were torn away from Europe and Africa by earthquakes and floods, and that the vestiges of the rupture reveal themselves if someone brings forward a map of the world and considers carefully the coast of the three continents. You know, pretty powerful stuff. But he was talking about a process whereby continents had moved apart from each other. This was, you know, this is 400 years ago. And so he's proposing what is essentially an early form of continental drift. And the early map makers continued to make note of certainly the sort of physical similarities between the continents. And then we come to the 19th century. So at the top, we can see Antonio Snyder Pellegrini, who was a French geographer, who also had ideas about continental drift. He looked at the similarity of plant fossils between especially Europe and the US, and he proposed that all the continents were once together. So these are his drawings. On the left, this sort of single continent of the known world, and then they split apart. Which, if you look at modern reconstruction of past supercontinents, as we will do later, doesn't seem that far from modern reconstruction. So they were really thinking about the idea of a movable Earth. And if you think going back 150 years, you know, this idea that the continents could drift must have been really quite left field and quite revolutionary or completely, maybe just completely insane ideas. You know, the Earth was considered to be pretty immutable. And another scientist who was on the idea of continental drift, again, years before any mechanism to actually force this to occur, for any mechanism that drove this, was Charles Darwin, who trained as a geologist. And he noticed in the 1840s that coral reefs, and this is a picture of coral reefs on an atoll, he proposed a theory of how coral atolls are formed, that the circular reefs are formed by coral forming on a volcanic island, and then the reefs grow as the island subsides beneath it. So he had this idea of subsidence of buried land masses, so some kind of vertical movement of well, I mean, these are sort of buried continents, really. But again, you know, there was no mechanism. No one really had formalized any idea about continental drift until we got to Alfred Wegener, that someone mentioned earlier. So Wegener is really, so he was in the early part of the 20th century, and he's really credited with the first to formally propose a theory of what at the time was referred to as the continental drift. He was a German meteorologist, and his book, The Origin of Continents and Oceans, was published in 1912. And it's widely accepted as the beginning of the modern idea around plate tectonics, even if the theory was only formalized 40 or so years later. And the main idea was that modern continents formed a single landmass in the past, and this was founded by simple observations such as, again, the coastline fitted, the patterns of fossils in similar sedimentary rocks across different continents. So he'd not only looked at South America and Africa, but by this time people had been globe-trotting, and they'd been cataloging rock records around the globe and trying to really link up different sedimentary sequences. Before we could date rocks, the only way we could look at we could understand the relative ages of rocks, really in sediments and through the relative position that they held within a sedimentary sequence. And so a lot of people spent time in trying to match different vertical sedimentary sequences across continents and across countries, for example, to try and understand how things fitted together to build up a modern stratigraphy. So they noticed that fossils, which were very good for dating strata, because fossils exist in a period of time and they evolve, and so a specific form of that fossil can give you some kind of relative date. Again, in 1910, we didn't know how old the Earth was. We couldn't reliably date a rock at all. So everything was about relative ages. But, you know, Wegener noticed that you could find similar fossils across different continents that now were separated by oceans and ocean basins. So Wegener was Can you hear me? Can you hear me?
Yes, we can hear you.
Sorry, I had this thing popped up telling me to unmute, so I'm muted again. Okay, thanks. Okay, I'm doing this on a laptop, so I can only just see the screen that I'm sharing. Anyway, so Wegener lacked a mechanism to underpin his ideas, really. And so we came to the 1920s, and Arthur Holmes, who is known, I mean, he's a famous British geologist. He was originally a geochemist that studied the newly discovered science of radioactivity, and he tried to apply it to the project of dating the age of the Earth. There's a really good book called The Dating Game, which is a sort of popular science book about Arthur Holmes and about the attempt to try and put an age on the Earth. But Holmes realized that radioactive decay releases heat, and that radioactive decay probably meant that the interior of the Earth was molten. And at this time we knew about, or we had formalized this idea of the mantle to some degree. But he suggested the mantle to convection, that if the mantle was hot, and if it was molten, and if one way of losing heat is that you go through convection, that could well be a mechanism and the answer to Wegener's missing mechanism for continental drift. So you can have a continental block that can split apart, and it basically floats around on a molten mantle that's undergoing convection, and this drives the continents apart. So this was sort of an early attempt to try and put forward a mechanism to explain this continental drift. We kind of go through the Second World War when people obviously and clearly had other things that they were worried about. And really the story of Tectonics picks up after the Second World War, when atomic bomb testing became prevalent, when enemy powers were setting off atomic bomb tests in places like the South Pacific. And scientists put in a network of seismometers around the globe to try and pinpoint where the atomic bomb tests were happening. US scientists especially. Obviously, they're interested in what the Soviet Union were doing. And seismometers measure earthquakes. If you have a network of them, you can localize and try and understand where the epicenter of that earthquake is, and also the magnitude. So in an attempt to track where and the magnitude of the atomic bomb tests, the side effect was that this allowed the mapping and the distribution of earthquakes. We discovered that the Earth was far more active, and there were far more earthquakes than had ever previously been reported, and that these earthquakes pretty much drowned out the atomic bomb tests. And this is a modern map of earthquake distribution over the last 117 years, 1900 to 2017. The size of the size of the circle is obviously the intensity and the magnitude of the earthquake. But this shows that there is a particular distribution in earthquakes, and so this took people by surprise. You know, we're looking for atomic bomb tests. We actually discover the Earth is a lot more active. There are a lot more earthquakes than we previously thought, and they conform to a pattern. They're predictable in where they are, not necessarily when they happen. There are a range of deep and shallow earthquakes, but we can map them out. There's a systematic pattern, and they're along, again, the margin of Western North America and South America. We find them along the center of Asia. We find them very much in a distribution in the Western Pacific, from Japan down southwards as well. The other line of evidence that came, again, we're sort of building towards when plate tectonics as an idea really crystallized. So what else was going on in the 1950s were very intensive seafloor surveys. So boat-driven surveys, people were pulling magnetometers behind the boats, and they're also driving echo sounders to look at seafloor bathymetry and understand the topography of the seafloor. And these were systematic surveys that went across the ocean floors on grids to try and understand the subsurface, because people were starting to look at the oceans a lot more. And again, they found a pattern. So on the bottom left, you can see pretty much a sort of, at the top is magnetic anomalies. These are obviously, this is a modern diagram. If you go back, the data was a lot fuzzier back in the day, but you can see the magnetic anomaly on the top. So this is looking at the magnetism of the subsurface rocks. And then the bathymetry. So the depth of the seafloor as you go over the central Atlantic. And they discovered that there was an apparent subsea mountain chain up to 2.5 kilometers higher than the surrounding ocean floor, which is a significant height. And you could discover this all through the North and the South Atlantic. Again, on the right here is a modern bathymetric image of the Atlantic Ocean. You can see this very defined mountain range, this ridge that cuts its way through north versus south. And they saw a systematic pattern of magnetism, of magnetic anomalies, which is sort of deviation from the norm as you go across the ridges. So this idea of a sort of mountain chain in the heart of the oceans was pretty fascinating. And this idea of a magnetic anomaly, which we will talk about in a little bit more and what it meant, was really quite fundamental to understanding what these mountain chains were. So there was a lot of work mapping not just the Atlantic, but also the Eastern Pacific as well. So especially on the sort of North American margin. And so the next really, I mean, you may have heard these terminologies. So seafloor spreading, the next significant idea that really started crystallizing that again led towards the idea of plate tectonics was this idea of seafloor spreading that was proposed by Harry Hess, who was a US geologist, who was also a Navy submarine commander during the Second World War, where part of his mission had been to study the deepest parts of the ocean floor. And just after the Second World War, he had discovered many sort of ridges and mountains which shaped the Pacific floor. And then when these systematic surveys started discovering the Mid-Atlantic Ridge and the subsurface mountains, it inspired him to look back at the data from the 1940s. So he proposed in the early 60s, in 1962, that the movement of the continents was a result of what he called seafloor spreading. So he basically said that these mid-ocean ridges, these ridges that we find in the middle of the Atlantic, is where new oceanic crust was generated. And the trenches that we find, these deep trenches on the margins of, say, South America, are where oceanic crust was destroyed. And he said seafloor spreading, and this is a picture of Harry Hess with his sort of sketch on the chalkboard. The mid-ocean ridges is where the molten magma from the mantle could rise up, and as it cooled, it solidified, it would expand and it would push apart, and then new crust, new basalt would rise up again, and it would solidify and it would push apart. And this was his mechanism for not only building the mountains in the middle of the Atlantic and the Pacific, but also a mechanism for pushing the continents apart. And this way, the Atlantic Ocean would get wider, but the coastlines would not change because you're not altering the coastlines. You're basically widening the middle of the ocean basin. So this theory allows plates to move, the idea of seafloor spreading, and continents are attached to the plates. And most importantly is that it's predictive. So if Harry Hess is right, and you have the generation of new oceanic crust at the ridges that then spread apart, and then you have new oceanic crust, then you can say, well, why don't we test and say if the seafloor closest to the ridges should be the youngest seafloor, the ocean crust should be the youngest ocean crust, and that further away from the ridges on either side should be older. So it is predictable. And the hunt was kind of on, really. And then we come back to this idea of the magnetic reversals that people saw in the early bathymetric surveys, where we had these fluctuations, positive and negative anomalies. And on the right, this is a better sort of representation where you can see these kind of stripes. So here, if you can see my laser point, is the Mid-Atlantic Ridge. So again, this is the North Atlantic, South Atlantic here. This is sort of a cross section. And we have these stripes that represent positive deviations of magnetism and negative deviations of magnetism. So this is trying to look at the so that's in relation to today's magnetic field. So some are aligned with today's magnetic field, some are not aligned with today's magnetic field. And it's symmetrical across the ridge. We can find these stripes. And two English geophysicists, so Frederick Vine and Drummond Matthews, came along with the Vine and Matthews hypothesis in 1963, and they attempted to try and prove that Harry Hess was right with his seafloor spreading, and they did it by looking at the magnetic stripes and the magnetic anomalies that you find either side of where the seafloor should be spreading. And they published this paper in Nature in 1963, Magnetic Anomalies Over Oceanic Ridges, which was really kind of the crystallizing and the most important point when it all came together in terms of the theory of plate tectonics, because this was kind of the proof. And there is no Nobel Prize for geologists, alas, but this kind of work in another scientific discipline would really stand up well for a kind of Nobel Prize. And I can't really stress it enough that, in terms of geosciences, this is such a fundamental paper, because we'd been coming up towards the idea of what continental drift is, what seafloor spreading is, what could be happening for, 100 years, 400 years. Obviously, things were accelerating, and then Vine and Matthews came along. So what is the Vine and Matthews hypothesis? They were working at Cambridge. They were marine geophysicists. And they basically said that when ocean crust forms at mid-ocean ridges, a spreading center where you have seafloor spreading. So again, on the right here, where the laser pointer is, this is the mid-ocean ridge. The cooling crust will become magnetized in the direction of Earth's prevailing magnetic field as it cools. So what do we mean by that? This is a picture of Fred Vine, by the way, on the bottom left, and Drummond Matthews. This is in sort of the early 70s. So he was a graduate student, and Drummond Matthews was his advisor. So it's not bad to publish a Nature paper as a newly minted PhD student. It's kind of what we all aspire to. So let's go back to the magnetism. So this is a bit of a complex slide. I will work through it. But when basalt forms, so we say that basalt forms in the mid-ocean ridge. Basalt rises from the mantle, and when it cools through a certain temperature point called the Curie point, which is about 570 degrees centigrade, when it cools below that, it forms an iron-rich mineral called magnetite, and that will orientate itself to the prevailing magnetic field at the time. We all know that Earth has a magnetic field. As you cool basalt below 570, it will lock in the ambient magnetic field. Now, we know that the Earth's magnetic field flips every 10 to 20 million years. It will just do a complete 180. At the moment, I mean, it's wandering around the pole as it is. It's not stable. The magnetic field is basically driven by convection in the Earth's outer core, but it can flip. And so when you have this flip, the magnetic field will reverse. So as you slowly form new crust at the Earth's at the mid-ocean ridge, new basalt, and it cools, it will lock in the ambient magnetic field. Over time, that magnetic field will flip. So the new crust, the new ocean crust, the new basalt that's being formed at the mid-ocean ridge will then have a negative anomaly, because it will cool and it will lock in a different magnetic field. And then the Earth's magnetic field will flip again. So these magnetic stripes represent a historic record. It's like a tape recorder of the Earth's magnetic field flipping between positive and negative anomalies. And this is symmetrical across the mid-ocean ridges. And this was really taken to be the proof that seafloor spreading is happening, that we are forming new oceanic crust at the center, and the crust is moving apart, and we can use the magnetic stripes essentially to date, because we understand how the Earth's magnetic field has flipped, and we can use that to date and understand how the seafloor has spread. Now we can send probes down to the bottom of the mid-Atlantic and collect samples, but it was very difficult to do that in the 1960s. So everything was being done through remote geophysics, like magnetism and sort of bathymetric surveys. So the Vine-Matthews hypothesis in the early 60s really was the thing that basically said, this is happening. This is the mechanism. Harry Hess was right. Seafloor spreading is right. This is a mechanism for continental drift. And this absolutely explains the age patterns of oceanic crust. So we go back to similar to the slide that we saw early on. At the top, you can see the youngest crust is in the red, the oldest crust is in the green in terms of oceanic crust. And you can see that, as you look at the margins of the continent, that's the oldest oceanic crust. In the center, it's the youngest. So this is seafloor spreading in action. This is the mechanism for continental drift. So it revived the idea of Arthur Holmes's theory of mantle convection as a driving mechanism. And I guess the other part we talked about, mid-ocean ridges, oceanic crust is formed, but also oceanic crust has to be destroyed. Unless your Earth is continuously expanding, you cannot create new oceanic crust all the time. You have to, at some point, destroy it. And the other side of the picture is the subduction zone. So the subduction zone is where oceanic crust, which is denser, goes underneath continental crust. And here's an image of, this is the downgoing oceanic plate here. As you can see, it goes down. This is a subducting slab. This is crust here and a continental margin. And this is, I mean, subduction zones themselves are very important geological features, because it's not only where you destroy oceanic crust, it's also where you form continental crust, because this drives magmatism and volcanism, because the oceanic crust that goes down liberates water when you hydrate. You know, if you form basalt on the seafloor, it's going to be 200 million years before it then goes down, before it then traverses across the ocean and then goes down again. It's been hydrated by the ocean. This flux is melting in the mantle wedge here, for example, and it forms volcanism and magmatism. And we know that above subduction zones, you have a lot of volcanoes, you have a lot of earthquakes as well. And this is where you create new continental crust. So subduction zones are destroyers. They destroy oceanic crust, which just goes back into the mantle, and it melts and it gets recycled back into the mantle. But it's also where we can form continental crust on the Earth because of this process of remelting of the mantle here. Someone told me the other day, I didn't realize that the entire ocean volume of water is recycled via this process every 8 million years. So it's an incredibly efficient way of taking water back down into the mantle and then driving it up through the atmosphere. And this is one reason why subduction zones are very important, because they are recycling factories. This helps drive the interaction between chemical elements between the interior of the Earth, the crust, and the atmosphere. And over the last 20 or 30 years, we've learned a lot more about how, you know, the Earth is a system as a whole, how the subduction and rates of subduction really have implications for the chemistry of the atmosphere and of the oceans as well. So subduction zones are very important. And really, you know, this slide tries to put it all together. So the idea of a spreading center and subduction zone. So this is kind of plate tectonics in a nutshell. We have rigid plates on which continents largely sit. We also have oceanic plates. You have two kinds of plates, really, continental plates and oceanic plates. The oceanic plates are young. They're represented by oceanic crust and continental crust. We form new oceanic crust at spreading centers, and then we destroy oceanic crust at subduction zones. We can create new continental crust at subduction zones as well. And plate tectonics is largely a cycle of oceanic crust creation and destruction. The continents, we create a little bit more continent on the margin, so we can get younger continental crust. We can destroy continental crust through subduction as well, but the continents are pretty immutable. They sit there, they watch the oceanic crust being formed and destroyed as well. We now think that the main driver for continental crust is actually what's called slab pull. So the gravitational pull of this downgoing slab here is so great that this pulls the mid-ocean ridge apart, which actually means that we melt new crust by melting the mantle. So you have upwelling of the mantle, which basically forms basalts at the center. So this is kind of the conveyor belt, if you like, of forming and destroying oceanic crust while continents sit on the margin. And really, what does that mean for the continents? So plate tectonics also includes this thing called the Wilson cycle, which talks about how ocean basins open and close over time. So on the right, we have this idea of a block of continental crust, here a continental plate, that can start to rift. So this is happening in East Africa at the moment, in the East African rift zone. You have an upwelling in the mantle, it's hot, it starts to thin, and then it starts to break that continental crust. So now you have two parts of continental crust, and you're forming an ocean basin. So over time, this is what will happen to East Africa. You will form an ocean basin, as we have in the Atlantic. You will start to form oceanic crust, which is here in the black. This is the thin oceanic crust pushing the continents apart. At some point, because this is not happening in a vacuum, adjacent to it, there may be another ocean basin that is opening or closing. That will eventually overcome the forces of extension of this basin, and it will start to close the basin again. And here in D, we're forming a subduction zone. So the continental fragment on the right is now being pushed back again, because to the right, we have another ocean basin that is opening. So now we have formed a subduction zone here, and we're closing this ocean basin again through subduction. And the final piece of the puzzle is that the ocean basin completely closes. And in F, we are what we call suturing. So we're now basically meshing the two continents back together. This is what's happening in the Himalayas. So the ocean basin between India and Asia has shut. We're now building mountains. And then the whole cycle starts again. At some point, that continental block will rift again, and it will open and close. So the Atlantic is where we are in C. We don't have any subduction zones on either side of the Atlantic. It's just opening up. The Pacific is in D. The Pacific is a basin that is closing. We have subduction zones on both sides. It is actually closing up. And yeah, my example for F is the Himalayas and also the European Alps. So Africa is charging into Europe. The Alps are still growing. The magmatism and the earthquakes that you see in the Aegean and in Italy is all because this is a closing ocean basin. So, critical observations which all pull together to, if you like, prove plate tectonics include things like the location of volcanoes and earthquakes. The volcanoes and the earthquakes are in a very predictable pattern. They're at the margins of plates. So in North and South America, we're obviously familiar with the South American Cordilleras and the volcanoes along there. There's a lot of porphyry copper deposits that are all related. The Aleutian chain, for example, we pop over here, the Western Pacific chain of volcanoes. That's where a lot of earthquakes are happening. A lot of earthquakes along the Alpine Himalayan chain, not so many volcanoes. But the location of that really shows you the boundaries of these plates. Obviously, the paleogeography that people first looked at to understand how things fit together, seafloor bathymetry, this idea of mountain ranges in the seafloor, magnetic stripes, the Vine-Matthews hypothesis, and the age distribution of oceanic versus continental crust. So all of these are critical observations that really came together at the late 60s, and people said, yeah, this is how it's working, and this explains everything, really. So the major plates look like this. There's about up to 27, depending on where you count, but largely you have continents at the core of them, and they dance around each other. So the different plates, or the different major plates here, are in different colors. And we have plate margins. So these in the black, you can see this is the North and the South Atlantic plate margins. You have variously complex margins where you are obviously accommodating plates moving on a sphere, which is what the Earth is. So it's going to be slightly complicated, constructive and also destructive margins. And in terms of how fast they move, this is sort of plate motion and velocity. So these are absolute plate motions. In I'm not quite sure. They obviously have a something against which that's all measured. But the length of the arrow is the speed, and the direction is obviously the direction the plate is going. So the plates are not necessarily all moving at the same speed. I believe as I've written there, the Atlantic Basin is spreading at about 1 to 2 centimeters a year, which is pretty much how fast your fingernails grow. The Pacific Basin in places is charging a bit faster here, but then it is subducting a lot faster as well. So there is a net closure of the Pacific Basin. So I wanted to then really, hopefully, I'm still keeping you with me. So I wanted to talk about, when did plate tectonics begin? I mean, we talked about the origin of the Earth earlier or the origin of rocky planets as material that had condensed from sort of interstellar material, and basically formed, it's again fireball really. But obviously, when the Earth was formed, you did not have operative plate tectonics, and we think that for the first 500 million years or so of the Earth's history, it was a magma ocean. It was a very hot, very molten ball. But the question that geologists are still struggling to ask is, how did you go from 4.5 billion years ago when the Earth was formed and it perhaps looked like this to today? What is the transition period and what does that evolution of the Earth look like? So just to remind you, I thought I'd put a geologic timeline here again. So this is perhaps a bit more attractive than the early one. So the Earth was formed up here at 4.55 million years. And then we work our way clockwise. So the oldest period is called the Hadean, up to about 4 billion years. I should say the moon was formed perhaps 4.5, 4.4. There's a lot of controversy about whether there's a young or an old moon, but for the sake of argument, the moon was formed just after here. And we think the moon was actually formed by the collision of a Mars-sized body with the Earth, which ejected material, which ended up forming the moon. That's the current model. Again, that relies upon a lot of slightly convoluted geochemical evidence, but that's the current model. So the moon was formed very early on. The Hadean era, which goes up to 4 billion years ago, was really when we think there was a magma ocean. So the Earth was fairly molten. It was undifferentiated, unlayered, apart from the core. The core formed and everything else was just very hot. But from 4 billion years onwards, we start to have what we would, as I said, our oldest rocks are about here, 3.8, 3.9 billion years. So we obviously were forming continental rocks at this point. So we really think about the evolution of the continents from about 4 billion years onwards. Life perhaps goes back to 3.5, 3.2 billion years, so around here in terms of single cellular life. The atmosphere really started to become oxygenated at between 2 and 2.5. So there's what's known as the Great Oxidation Event at about 2.4. And that really set the scene for multicellular life to develop much later here. Dinosaurs up here. But we're looking at a void of geological time. And the problem is that we only have the fragments of rocks left to try and understand what the planet was like. And the question is, at what point between probably 4 billion years ago and today did plate tectonics as we recognize it start operating? Again, this is kind of something I've worked a lot on Archean. So Archean, again, this is the period that goes between 4 and 2.5 billion years ago. I've done a lot of work on Archean rocks, which I find fascinating. And the thing about Archean continental rocks or continental crust is that they are different to modern continents. So you may have heard the term TTGs. This stands for tonalite, chondromite, granodiorites, but these are very peculiar granites that are very unique to the most ancient continents. So formed in the Archean, you have continental crust that is different to what we form today. And on the right, this is a distribution of TTGs. So the oldest are in the dark red, and these form what we call the cratons. So Western Australia, Southern Africa, Western Africa, North America, for example. This is Greenland. So these are really old rocks in the dark red. We have some in northwestern Scotland, up in the Louisian. We have some in Ferro-Scandinavia. But when you want to understand about, as I mentioned before, we form continental crust in subduction zones, but does that mean all continental crust was formed in subduction zones? And if you don't have a subduction zone, does that mean you have plate tectonics? And so people look at whether these continental rocks were formed in a subduction zone or not. And the fact that they are compositionally different generally points towards the fact that they probably weren't formed in a subduction zone. Why would you expect the early Earth to be different in terms of how it operated? Well, the main reason is that it was hotter. This is a complicated graph, but this is trying to show on the left here, this is millions of years from today. So we are here today. This is going up 3.5 million years. So the Archean era is here. Formation of the Earth is falling off the end here somewhere. And what this is trying to plot is predictions for the temperature of the mantle in degrees C. So we look at the right-hand axis. This is degrees C, 1400, 1500, 16. Present day temperature of the mantle is about 1380. The predictions are that way back at 3 billion years ago, the mantle was about 200 degrees C hotter than it is today. This is, I mean, again, there's a lot of error in this. If you take anything away from this graph, it's that the mantle was quite a bit hotter than it is today. And the point is that we create crust, we create oceanic crust, and we create continental crust by melting the mantle. So we melt the mantle to create crust. If the mantle was hotter, we will create different crust and we will create more of it. So, my feeling, again, is that way back at the start of the Archean, we formed crust in a very different way. I've done a lot of work in northeastern Australia. This is the Pilbara Craton. So we're way up here. If anyone knows Australia, Perth is down here, Port Hedland is here. But the thing about the Pilbara Craton is it has these granite domes. So this is the Mount Edgar Dome here. These stippled areas are granite domes. So these are some of the oldest pieces of continental crust on Earth, the oldest TTGs. And people think that they formed in what they call vertical tectonics. Again, I don't want to go too much into the detail. I could talk to you about this for half a week, and I've only got 10 or 15 minutes. But I suppose, again, the take-home message is that the earliest continental crust, we think, maybe 3.5 billion years ago, was not formed in a subduction setting, but it was formed in an oceanic plateau setting, in a vertical tectonic setting, because it's compositionally different, it's structurally different, and it's surrounded by a lot of relic oceanic crust. At about 3 billion years ago, again, if people want to ask me questions about that, that's fine. But there's a lot of geochemical shifts at about 3 billion years in terms of the composition of the crust, in terms of other things that point towards a significant and a major tectonic shift happening on the planet. Again, I don't want to go too much into this, but this goes from 4 billion years to 0. There's a big shift here that shows that the continental crust is getting more silicic, it's getting more granitic. On the right, these are inclusions in diamonds. Again, we're seeing these eclogitic inclusions, which is related to subduction type activity from 3 billion years onwards. So there seems to be a shift at about 3 billion years. So if we go back to the reason why we're talking about this, is this idea of how the Earth evolved and when plate tectonics began. So way back at 3.5 billion years or 3,500 million years, we have these early TTGs, continents, and at some point they start to accrete together, they start to form proper continental crust and continental plates, and that happens at about 3 billion years ago. So that's probably when we think plate tectonics in some form kicked off. It hasn't happened, it hasn't been operating forever, but it's probably been operating for about 3 billion years. And for example, the rise of atmospheric oxygen at 2.2 is probably not coincidental in that, if you form stable crust, if you form these stable tracts of crust through horizontal tectonics, then you give platforms for life to evolve. And the earliest single cellular life was important for actually oxygenating the atmosphere because they worked off photosynthesis. So one more thing I will cover before I confuse all of you. How do we date rocks? We use geochronology, which is based upon radioactive decay. I'm particularly interested in using these minerals called zircon, which you can find them. I can go down to the West Sands and I can find thousands and thousands of zircon crystals. These are tiny. So this is an SEM, an electron microprobe picture of a zircon crystal. There's about 10 of these to a millimeter. These are absolutely tiny, but they're very common in granites and continental crust. And we can date them using uranium-lead geochronology, using radiogenic isotopes. So what we can do is go to river sands and sediments, and we can separate out zircons, because when granites weather, the zircons survive, so we can look at the age distribution of crust through time. And what we find here is that if we date all the zircons, this is a database of about 500,000 zircons from all around the world, we see peaks. And what these peaks mean is that we had major phases of continental crust production at different points in Earth history. So it hasn't been linear. We haven't had continual crust production, but we've had episodic crust production. And you know, I said that continental crust on the modern Earth in this time frame is formed in subduction zones. So we seem to have had significant subduction activity at 3 or 4 or maybe 5 periods in Earth history. And this is related to what's called the supercontinent cycle. So the Earth's continental plates are dancing around each other because of the operation of plate tectonics. And we've talked about Wilson cycles, where ocean basins open and ocean basins close. And really, I suppose the important slide is here. The supercontinent cycle describes the fact that at certain periods in Earth's history, all the continents come together and then they split apart. So you have these Wilson cycles that open and close ocean basins. The most recent supercontinent was Pangaea. These episodes in crust production we see in the zircon ages relate to formation of supercontinents and then the destruction of supercontinents as they open and close. So that's really what I wanted to talk about. You know, there's a lot of things. I have a little, I can make it work, a little video here about the next supercontinent. See if this can work for people. So this is a prediction over the next 150, 200 million years ago about how, for example, the Earth's continents may ultimately move to form a new supercontinent. So my message is that the Earth is continuously evolving. Oh, hold on. How do I get to the next one? The Earth is continuously evolving. You know, the distribution of the continents that we see today is only transitory because they are always moving around. Plate tectonics started maybe 3 billion years ago, and since then we've seen about 3 or 4 major supercontinents, and it's all driven by plate tectonics, by this idea of ocean basins closing and opening, the idea of seafloor spreading, forcing the ocean basins to open, and then the basins closing again through destruction of oceanic crust through subduction zones. So there we go. That was my talk today. Hopefully I haven't confused you all. I'd love to help you out with any questions, and thanks very much for your time. Thank you. How do I do stop share? Hold on. All right. Right, there we go.
Okay, Nick. Well, thanks a lot for that. That's given us a huge and rapid tour through a very, very long period of time, and refreshed our memories on some things, but give us a lot of new material to think of as well. I think there are going to be quite a lot of questions coming up. I know there's a few on the list, and more will probably emerge as we discuss. One question that I had been thinking about, and which I think you may have partly answered as you went along, but which I will ask anyway, was that I remember about 30 years ago when I was going around the Geological Museum in South Kensington. There was an exhibition there about plate tectonics, and it pointed out that not only do all the continents fit together on the Earth's surface, but that if you imagined a much smaller Earth, all the continents would fit together as a closed sphere on a smaller Earth. It didn't draw any conclusions from that, but it sort of left you to wonder whether it was suggesting that there had been a time when the Earth had a continuous solid crust on its surface and was much smaller, and then perhaps unwisely swallowed an asteroid or something and burst itself and left it in the state it is today.
Yeah.
Has that idea had any currency, and does it mean anything, or was it just a deviation in people's thinking?
Yeah, thank you for the question. No, so there is this thing called the expanding Earth theory, which raised its head a while back, and I think still has. There are still some proponents in some quarters, but I think most mainstream geologists have sort of dismissed it now. That this idea that the Earth, if you're opening ocean basins, then if you continuously expand the Earth, then that would explain all the ocean basin expanding and the continents drifting away from each other. But there's a couple of problems with that. First of all, obviously, as you say, if the Earth expands, you have to explain why it suddenly got a lot bigger. So does that mean that you have had a significant asteroid bombardment? Well, the first thing that would do is destroy all the evidence on the planet for having continents in the first place. You're kind of resetting things anyway.
Yes.
And the second thing is that we don't need to invoke that, because we understand that we can have a constant size Earth, and we can destroy oceanic crust, and we understand through things like paleomagnetism, which are reconstructions of where the continents have been through time. So we can find in terms of latitude and longitude that these things have actually danced around, and so we can do full-scale reconstructions, even though we've lost the ocean basins, because that's all gone in the past.
Yes.
We can try and pin down where the continents were at different periods in Earth history. So yeah, I mean, you're right that there had been some idea about an expanding Earth theory, but I think that's well been superseded because we don't need that idea to explain what we observe anymore. Exactly.
Because I wondered if it was one of those things that sort of sunk quietly over time. But yes.
Pretty much, yes. It always seems to appear from left field sources, but I think no, I don't think I haven't heard. Yeah, I haven't. I probably last heard it about 5 years ago. I think it sort of came, but
the implication was not as an alternative to ocean floor spreading, but as an explanation for the existence of continental crust in the first place.
So there is some idea that. So yes and no. So it is very curious that why is the oldest continental crust we find just after the late heavy bombardment? But we think the late heavy bombardment was about 4 billion, 3.9 billion years ago. So this is the last significant sort of shower of meteorites that hit the Earth. Again, the idea of a late heavy bombardment, most of the evidence comes from crater counting on the Moon. And so there are some space scientists who don't even believe in the late heavy bombardment. But if you take that as a fact, then it is interesting that if there was anything that existed on the planet before, perhaps it was wiped out. And maybe the reason why we don't see any older continental crust than 3.8, these early TTGs, as I said, could be because they've all been obliterated by sort of meteorite showers. But there's also an idea that you could form crust through meteorite impact. I mean, I mentioned that crust comes from melting the mantle. The one way of doing that is you have an impact, and that obviously causes a big thermal anomaly where you hit, which could generate low pressure, high temperature melting. So that's an idea, yeah, absolutely. But not as a general mechanism for forming crust, because we have other candidates that's more reliable, if you like.
Well, thanks for that. I know there's lots of other questions now, so I think that they will now pop up in front of you.
Oh God, there's loads. Right. Clearly, maps of various kinds have played a key part in triggering and confirming theories. Can you say something about the development of different technologies for exploring and confirming plate tectonics and ongoing changes to the crust in more recent years? No, that's a great question. So I suppose I'm a geochemist, so I mainly have a geochemical view of things. I mean, there's been a lot of work in, as I mentioned, paleomagnetism, which is not my area of expertise, but in terms of trying to do proper plate reconstructions through Earth history, there's been a lot of work in the paleomagnetic world. What we have looked at is a lot of different isotope systems. So not only do we use radiogenic isotopes for dating rocks, so we measure the ratio of parent to daughter isotopes, and then we can work out how long that decay has happened and therefore date a rock. But we can use these isotopic systems to trace geochemical and geological processes, most specifically crustal formation processes. So when you form crust, it's a process of distillation, if you like, differentiation, and that affects isotopic systems. So there's been a lot of work, especially in terms of high precision in situ analysis to look at these isotopic systems. So I showed that picture of the zircon, which is 10 of those to a millimeter. You know, you can now go into those zircons where look at the growth zoning, and you can measure different isotope systems. So there has been a lot of work to try and understand, because you can date that precisely and then use these different geochemical tools to try and look at what the crust was like and the formation mechanism. So to try and build up big pictures for that. So I think, you know, the new technology has really been in terms of analytical tools. People are now looking at things like, we use ion probes. There's an ion probe in Edinburgh, which again is a, you know, $2 million piece of kit that only a few universities can have, but they are very precise in terms of measurements. People are also doing a lot more geodynamic and computational modeling. So trying to look at what the structure of the Earth could have looked like, and how, if you're looking at mantle convection and things like that. So really sort of, you know, 500, 1,000 kilometer scale simulations of how the crust and the mantle could work with each other. And these are quite computationally intensive, but obviously as we get more powerful computers all the time, we can run these models, or I don't, but my colleagues run these models a lot more. So I think these geodynamic models, so long as they're grounded in real observations, because otherwise you can go off into sort of the realm of fiction, can be really powerful, because we only have what's left on the surface of the Earth to tell us about 100 million years ago or 1,000 million years ago. So to try and get that third dimension, the depth, and trying to understand the mantle and the crust relationship, which is, you know, really is the heart of plate tectonics. I think the modeling is really good. Okay. Oh, yeah, the next one. This is a very big system, bigger and denser than atmospheric or oceanic circulation. And you're at COP. How do you see tectonics being influenced by climate change? That is a very interesting question. So about 20 years ago, people started investigating the relationship between tectonics and climate. And people specifically, for example, the rise of mountain chains like the Himalayas, the enhanced weathering of those mountain chains, and what that means in terms of CO2 drawdown. So the Himalayas are, you know, you find limestones in ocean floors. Then the Himalayan chain, much of that is made of limestone because it used to be at the foot of an ocean. When you weather limestone, you can lock down CO2, or you can release it, for example. So this relationship between, if you like, active tectonics, weathering, surface processes, and what was happening in the atmosphere has been looked at. And also things such as climate forcing. So we know that volcanic activity can have short-term effect on the climate. That's driven by tectonics, for example. I think it's definitely, I mean, we have a number of researchers at St Andrews that are looking at past and future climate and how that relates to the solid Earth. And I think that's definitely an area that people are looking more at the moment and trying to understand. Again, you find that people have been on these different disciplines, and that's the way they work. But what you need to do is get the climate scientists to work with the solid Earth scientists, I think. So the more we understand about the world as a system, I mean, tectonics works on different timescales to climatic systems, for example, but the Earth is a system, and as we look through the geologic record, we do see that certainly on a first order basis, there is a lot of link between what's happening in the deep Earth, the surface, and the atmosphere, and I think undoubtedly there must be some kind of link. When did the oceans form? Well, if that question is when did we have water on planet Earth, then right back to the start. I mean, again, I think if once the Hadean got out of the way, when everything was probably water vapor, presumably we had some kind of atmosphere. Again, everything is speculative once you get that far back, but we think that even those early rocks at 3.8 billion years ago were probably formed in a submarine environment. And that the continents only emerged from the oceans perhaps 3 billion years ago, or maybe 3.5 billion years ago. So again, in my field, a big area of interest is when these little tracts of continents became stable enough and emerged from the oceans, really. So there has been oceans and water on planet Earth, as far as we're concerned, for as long as the surface conditions have allowed that water to be water rather than vapor. More. Right, okay. Clearly, maps of various kinds have played a key part in triggering and confirming theories. Is this the one? I think we found that one already. Okay, here we are. Is plate tectonics, from Tom, is plate tectonics a necessary feature for the existence of life on Earth and elsewhere? So I think it's hard to say if it's necessary. I think it's easier to say or make the case that life on Earth, as we know it, the sort of crucible of where that life formed, if it was either Darwin's warm little ponds, can be very closely linked to what we think of as sort of environments formed by plate tectonics. I mean, I think what you need for life on Earth is you need some sort of volcanic activity, because that's a driver in terms of energy and in terms of chemicals. You need some sort of stable platform for that life to evolve on, and you probably need water. You need that to be in a submarine environment. And whether that's in what we think of as a sort of mid-ocean ridge setting, so people talk about the idea of black smokers and that these could have been a sort of crucible for the first life to develop, or whether it was actually on maybe a very shallow submerged continental platform with some sort of volcanic activity, like a hot spring or something like you might find in New Zealand, was put slightly below the sea, is debatable. Neither of those things necessarily need plate tectonics. What they need is an active Earth that has a volcanic system and has an aquatic surface on it. So, you know, I think that life probably formed on the Earth before we had plate tectonics. So I don't think plate tectonics is necessary, but some people would make the case that you need those kind of settings, and those kind of settings inevitably mean that you have plate tectonics. So again, people have stand-up debates in scientific conferences about these things. But I suppose if the sort of what that question also implies, you say on Earth and elsewhere, is do we need plate tectonics for life? I don't think that's the case, but I think, you know, those ingredients of some sort of volcanic activity which provides energy and chemical potential, which is the driver for these chemical reactions that ultimately form life. I mean, people look at things like Europa, which is one of the moons of Saturn, I think. Oh, it's getting late. Saturn, which is thought to have volcanic activity and an ice. You know, it's basically an icy moon, as potentially somewhere where life at similar settings could exist, sort of under the ice. So I think and again, that sort of life as we understand it, carbon-based life that we find on Earth. So good question. Yes, I've heard of cratons before. What are they and why? That's from David. Okay, so
you've partly answered it, but it would be good to summarize it as well. Yes. So kraton was first coined about 100 years ago by a German called Leonhard Kober. And so it comes from the German kratogen, which means rigid crust. So he defined this idea of kratogen and origin. And we still use origin or orogeny today for mountain building. So he talked about rigid crust versus deformable crust. We still use the term kraton to talk about these nucleuses of the continent, which have very thick crusts. So if you remember, I talked about the lithosphere that could be up to 250 kilometers deep. They're usually cored by very old crusts, so people call them the Archean cratons. They're very low heat flow. That's where you find diamonds, and they're potentially indestructible. So when you look at the distribution of Earth's plates, they're almost all cored by these ancient cratons, which then have younger crust that has formed around them. But, you know, to get subduction working, you need something that's not going to move. You need to be able to
push the oceanic crust under the continental crust. And this idea of getting rigid continental crust that's stiff enough that it's not going to buckle in the face of the oceanic crust coming into it is really important. So the idea of cratons as these sort of solid, rigid cores of continents that were formed early on in the Earth's history and have just hung about ever since then is quite a compelling one. So that's really what a craton is, this sort of thick continental crust, continental lithosphere, generally very old. That's again where you find the diamonds, because diamonds they have to form deep in the earth, and only the cratons are thick enough for the diamonds to form at the foot of them. When did the oceans form? I think we've had that one.
We have.
How far since 1413 has St Andrews moved? Good question. I guess in terms of distance, not in terms of intellectual capacity or otherwise. I've actually no idea. I would say, I mean, if we're moving at 2 centimeters a year, and that's 600 years, then that's 12 meters. Is that right? Something like that. So maybe we've moved 12 meters. So my office could have started near the coffee room, and it's now where it is. Verbal question from Basim Kenny. Question 7. Basim has got his hand up. Basim Kiani? Ah, yeah.
Hi.
Hey.
Firstly, I'd like to say thank you so much for your very informative presentation.
Thank you.
No problem. I had a question about, I was wondering how exactly does the angle that the lithosphere makes relative to the horizontal affect the surrounding convection, apologies, and how exactly would that affect the intensity of the volcanoes?
Can you repeat that? You sort of froze for a moment.
Sorry. So I was wondering, you know, when the lithosphere moves, first it's horizontal and then it subducts, right? And I was wondering, at the angle that the lithosphere makes relative to the horizontal, I was wondering how that affects convection and how that would affect the intensity of the volcanoes.
Good question. It just so happens I might have a slide to talk about this. And this wasn't a prompted, pre-planned question, honest. So I think I have it here. Here we go, subduction styles. So, yeah, so the angle of the slab. So we're looking down here, mature Phanerozoic. Well, this is an island art, but again, this is, so the Phanerozoic is essentially the modern style of subduction. So it's steep subduction. And what's really important about that is we have this thing called the mantle wedge. So the mantle is in the purple. You can see the oceanic crust is the green. And you're talking about this angle, I suppose, here, which is about 30 degrees or so. And that angle is quite important because the volcanoes, the magmatism that occur above the wedge, come from melting of the mantle. So we're not melting the slab. The slab devolatilizes. So as it heats up, the hydrated surface of the slab lets go of its water. That water fluxes the mantle here, which is this sort of pink stuff. And it's the mantle melting that then forms the crust above it. So in a modern subduction system with a steep slab, you have this idea of mantle melting. And that's really important for the style and the nature of the crust. So the modern continental crust, you know, I said that modern crust is compositionally different to older crust, is because that crust is formed in this mantle wedge. Now, we think that steep subduction was unlikely to happen back in the day. So even if you had some sort of early subduction on the early Earth, it was much more like this. So because the crust was not necessarily as rigid, we feel it kind of just stacked up. You had a lot more oceanic crust. And so you didn't have that concept of a mantle wedge. So what you were doing was you're actually melting the slab directly rather than the slab melting the mantle. So the long story short is it does matter. That's a really good question. And we think the angle has changed over time. And some people say that, yes, there was subduction, therefore plate tectonics 3.5 billion years ago. but the subduction was shallower, and so we're melting something different, which is why the early crust was compositionally different. Excellent question. Hopefully that answered your question. Yes, so please could you explain what was meant by vertical when talking about early continental crust formation? Yes, so in the context that we talk about vertical versus horizontal tectonics, so plate tectonics is horizontal tectonics. Things move around like this, things bump into each other and subduct. The idea of vertical tectonics is really that you formed continental crust in a vertical plateau setting. So I'll just share the screen again. I'll go back to this one here. Slideshow. Oh God. How did that go? I'll just do it. Yeah, so vertical tectonics, it's this idea on the right here, you see this sort of thick plateau. So the way the model goes is that the mantle was hotter. As the mantle melted, just like you find in a mid-ocean ridge, it creates basalt, and it continues to melt over. That basalt is not moving sideways like you find in a mid-ocean ridge, it's just sitting there. And so what you do is you build up an oceanic plateau, which is kind of this green blob here. This is an oceanic plateau that can get to maybe 50, 60, 70 kilometers thick. So modern oceanic crust is 7 kilometers thick. These are much, much thicker plateaus of crust that are just building up in situ. So you have continual volcanism over the top, these little volcanoes, and then you build up the plateau. And eventually that crust will get thick enough that it internally remelts. So continental crust is remelted oceanic crust. Early continental crust is remelted oceanic crust. So what you do is, instead of forming that continental crust in an arc type setting, in a subduction setting, you basically remelt internally that plateau. And so if you like, the model for the Pilbara, where you have lots of these different granite domes, so that these are rising diapirs, rising balloons of granite rock within an oceanic plateau. And they said that kind of thing could never exist on the modern Earth because it's not hot enough anymore. We can't build up these incredibly thick plateaus, and also we now have the idea of spreading. So if you form oceanic crust, it goes. It doesn't have the times of sort of over 400 or 500 million years, which are the timescales that we talk about on the early Earth, which is a phenomenal amount of time for it just to sit there, slowly get thicker and thicker. And then you get to the point that at the base of the plateau is hot enough because of the ambient heat, the geotherm, the ambient heat at the base of the crust, that basalt just remelts and creates continental crust. So that's the idea of sort of vertical versus horizontal tectonics. Vertical is this idea of plate tectonics, horizontal is things just build up, and then we form early crust in that. Hopefully that was... Gordon Freeman. When I was at university in the 60s, continental drift was measured by the variation in voltage caused by strain across intercontinental telephone cables. Did this work contribute to the measurement of the rate of continental drift? I've absolutely no idea. I've never heard of that. It's fascinating. I guess yes. If you put cables across the Atlantic, then over time. I mean, I suppose over time. But wow. I mean, that seems quite. Again, you know, we're talking about 1 to 2 centimeters a year. So not that I've heard of. No, fascinating. Well, Jabraith, apologies if I haven't pronounced your name correctly. On an early Earth before tectonics, but with volcanoes, what would the circulatory system have been instead? If you're talking about mantle circulation, so all of this, all tectonics, plate tectonics, it's all an expression of heat loss for the Earth. The Earth has to lose heat. Not only does it get cooler from its early elevated state, but also it generates heat through radiogenic decay internally. So it's always losing heat. The Earth over time is getting cooler, but it's still generating heat. So we think that obviously in the modern Earth, there is some circulation in the mantle that is convection. And we presume that was also the same on the early Earth. But these sort of oceanic plateaus, we didn't have an entirely, it didn't entirely cover the Earth in oceanic plateaus. Presumably, there was some way of circulating in some way. We honestly don't have any idea. I mean, people, as I said, people try to do geodynamic models. I don't think I have a picture of that as to what the mantle may have done. We assume it was a lot more vigorous because if things were hotter, things were moving a lot quicker. But yeah, good question. I don't know. Why has the outline of continents apparently changed so little since the breakup of the latest supercontinent? So in terms of, if you think about the Wilson cycle, all you're doing is you're just pushing things apart from the middle. So you're rifting in the case of Africa and South America. You have initiated the opening of the ocean basin by rifting it, and then you're just moving things apart. So the only thing that's going to change the general shape of that is if somehow, as it goes round the round Earth, then the geometry has to change in some way. But very, very crudely, those shapes don't have to change. And then maybe if they close up again, but they could close up again in a different way. So the outline of continents, we wouldn't expect them to massively change as you open an ocean basin, because you're literally just sort of passively pulling apart. And if you think in East Africa, you can kind of see that you've got fairly linear new continental margins as that opens apart. When the mantle was hotter, was continental movement faster? Joe Stewart, presumably yes. Presumably the Earth was hotter, it was losing heat more vigorously, circulation was more vigorous, cross production was more vigorous, so we assume things were moving a lot faster. There we go, the final question, I think. How did I do?
Well, I think you've certainly stimulated us a lot. There's been lots and lots of questions.
Thank you. Yeah,
and it's obvious that we've all been getting really stuck into this. So thanks ever so much. We've really enjoyed that, Nick, and I'd like to hand over now to Tom to propose the vote of thanks.
Well, I think I speak for everyone by saying that was absolutely fabulous. 6 months ago when I was scouring the internet looking for speakers and I came across this idea of plate tectonics, I thought that would be a really good subject. But what impressed me tonight was when you pair a good subject with a good speaker, it's a fabulous combination. I mean, well done. So that was very clear, very well explained, and you pitched it perfectly for a mixed audience like ours. So very well done. Honestly, I think that was one of the most kind of enjoyable and interesting talks that we've had in this series. So very good. I'm very, very pleased, Nick. So assuming everyone agrees with me, so anyway, I think that we should show our appreciation. And if you want to unmute yourselves, folks, please unmute yourselves and clap, cheer, say whatever you want to say. And thank you very much, Nick. That was great.
No, it's a pleasure.
Thanks a lot.
Very much. Thank you.
Thank you.
I appreciate the interest.
Many thanks. Thank you.
Great.
Good. Well done. Well done.
Brilliant. Well, thanks very much. I appreciate it. It's great to see everyone turning out, and it's always good to spread. It's a subject I find interesting, and hopefully,
yeah. I think we all find it interesting. After all, we live on it. It's underneath our feet, and yeah.
Great.
Yeah. So if anyone wants to say anything, please do.
Well, get back to my wine.
Yeah, good idea.
Tom, I have a question.
Oh, Gordon, yes.
I tried to get it through chat, but it didn't work. But when do geologists think the next magnetic reversal might occur?
Oh, wow. Well, good question. I don't know, but I know things are starting to wander quite a bit. So
I've heard about this, yes.
because they don't, it doesn't just, it's not like Sunday afternoon at 2:30, it's just going to do this. So the pole starts to become a bit unsteady from what I understand. And then it will over geological time reverses. So if I don't know if we will, in the next 100 years or 500 years or 1,000 years actually live through that, but I think the process of that magnetic reversal will be quite all the people doing their DoD gold awards and trying to work out
Yes.
they get very confused. So yeah, I'm not sure.
Okay, I have another question. I love going to Tokyo. I used to work there. I love it. I went every year. When's the big one coming?
If I knew that, I could make a lot of money, Tom.
Yeah.
It's always another. I mean, that's who knows. We're trying to get better at monitoring and predicting these things, but the Earth is in short-term timescales very unpredictable. But people look at volcanoes expanding and try and work out when the next eruption is. But earthquakes, they look at strain. Actually, there's and I know it's getting late, but people they put networks with GPS, very high precision GPS, especially around Japan. You can see Japan flex and strain, and so I think they're trying to understand how, as I said, an earthquake is when you get some period of elasticity and then things just suddenly break. It ruptures, so you build up that strain and then you break it, because it's not just moving like this. So can you monitor how the land literally deforms like a sort of it plastically deforms? Can you work out when you're at that point that you've kind of reached a critical point? I think that's probably where it's going, but that's a little bit out of my side of the area. But yeah.
Yeah. Okay. All right. Well, folks, I think that was great.
Yes, it was indeed.
You can all go fill up your wine glasses now.
Thanks to everybody and good night to all. See you at the next one.
Thanks again. Yeah.
Bye-bye.